Hi Professor, we are from Group 1. Today we are going to give presentation on FlowDroid, precise content, flow, field, object sensitive and life cycle aware taint analysis for Android apps. Coming to the abstract, today smartphones are ambiguous source of private and confidential data. At the same time, smartphones are targeted by carelessly programmed apps that leak information data by accident and by malicious apps that exploit their given privileges to copy such as data intentionally. While existing static taint analysis approaches have a potential of detecting such data leaks ahead of time, all approaches for Android use a number of coarse grain approximations that can yield a high number of missed leaks and false arms. In this work, we present FlowDroid, a novel and highly precise static taint analysis for Android applications. A precise model of Android lifecycle allows the analysis to properly handle callbacks invoked by the Android framework, while context flow, field, and object sensitivity allows the analysis to reduce the number of false arms. We also propose Droid Bench, an open test suite for evaluating the effectiveness and accuracy of taint analysis tools specifically for Android apps. As we show, as we show through a set of experiments using a Droid Bench and a set of well-known Android test applications. FlowDroid has a very high fraction of data leaks while keeping the rate of false positives low. On precision outperforming on commercial tools, IBM apps can source and forfeit SCA. In those, FlowDroid successfully find leaks in a subset of 500 apps from Google Play and about 1000 malware apps from a virus suite project. When coming to the overall introduction, Android has a constantly growing market share in the mobile phone market, which is now 81%. While Android phones are being ubiquitous, they became a worthwhile target for the attackers and users' privacy sensitive data. This privacy sensitive data is targeted by the hackers to steal their sensitive information such as location information, contact data, pictures, SMS messages, etc. But even applications that are not malicious and were carefully programmed may suffer from such leaks. For instance, when they contain advertisement libraries, many apps developers include such libraries to obtain some remuneration for their efforts, but few of them fully understand their privacy implementations. They are able to fully control which data these libraries process. Common libraries private informations that identifies a person for targeting advertisement such as unique identifiers, example IMEI, MAC address, etc. and country location or location informations. Android has a permission based security model. When coming to the permission based security model, before specifically discussing permission based access control, we can explore what permission really means. Conceptually, providing permission to a user means allowing him to access a resource or execute a specific operation in a system. Usual permissions related to reading, editing, and deleting operations on a given digital resource. So getting permission to access a resource means that at least the entity can read its content. In such a scenario, full access to a resource consists of having three different permissions, one for each permission read, edit, and delete. So we can understand permission based access control as the technique that defines specific permissions for every entity using a system. As previously stated, each permission typically is a tuple indicating both a resource and an operation. However, the fine-grained permissions control, also understood as a problem, it occurs since we need a personal management of these permissions of each entity. In this context, permission-based access control is an impartial for systems which lot of users due to manageability challenges it opposes. And coming to the large variety of sensors like GPS allows a context sensitive user experience, and they also create additional privacy concerns if used for tracking or monitoring. And coming to the introduction, Android applications are privacy violations which leak sensitive information such as location informations, pictures, SMS messages to the attackers. And for this, we proposed a taint analysis. The taint analysis address this problem by analyzing applications and presenting potentially malicious data flows to human analysis or to an automated malware detection tools, which can decide whether a leak actually consists of policy violations. The approaches track sensitive tainted information through an application by starting at the predefined source. An API method returning location information and then allowing the data flow until it reaches a given sink. While static code analysis do not share these problems, they run the risk of being imprecise as they need to abstract from program inputs and to approximate runtime objects. This precise modeling of a runtime execution is particularly challenging for Android apps as those apps are not standalone applications but are actually plugins to the Android framework. Apps consist of different components with a distinct life cycle. During an app's execution, the framework calls different callbacks within the app, notifying it to the system events which can start, pause, resume, shut down the app, etc. The analysis can inspect the app both dynamically and statically. However, the dynamic analysis program require many test runs to reach appropriate code coverage. Moreover, current malware can recognize dynamic monitors as an analyzed app executes, causing the app to pose a begin program in these situations. While static code analysis do not share these problems, they run the risk of being imprecise as they need to abstract from program inputs and to appropriate runtime objects. The precise modeling of runtime execution is particularly challenging for Android apps. During the app executions, the framework calls different callbacks. Like like any applications written in Java, Android apps also contain uh, aliasing and virtual dispatch objects. The FlowDroid analyzes the apps, the bytecode and configuration files to find potential privacy leaks either caused by carelessness or created with malicious intention. Fast data flow analysis approaches for Android handles the above challenges in an unsatisfactory manner using gain over as well as under approximations. And in this work, therefore, we present FlowDroid, a never static analysis system specifically trained to Android platform and based on a novel on demand algorithms that yield high precisions while maintaining acceptable performance. FlowDroid analyzes the app's bytecode configuration to find potential privacy leaks to obtain deep context. and object sensitivity while maintaining a acceptable performance. FlowDroid uses a novel on-demand aliases analysis. The analysis algorithm is inspired by Andromeda but improves over Andromeda in terms of precision. We have open source FlowDroid in summer 2013. The tool has been picked up by several researchers groups, and we are in contact with the leading producer of antivirus tools who plans to use FlowDroid productively in the analysis backend. For us and the others to be able to measure scientific progress in this important field of research, it is required that researchers are able to conduct comparative studies of Android taint analysis tools. Unfortunately, up till now, there exists no benchmarks that would allow the systematic studies. As another contribution of the work, we thus make available Droid Bench, and it is also one of the naval open source micro bench suite for comparing effectiveness of taint analysis for Android. And coming to the motivation, increasing chance of potential data leaks in Android apps. Coming to the potential data leakage, the data leak is when sensitive data is accidentally exposed physically on the internet or any other form, including lost hard drives and laptops. This means a cyber criminal can gain unauthorized access to the sensitive data without effort. While the terms data breach and data leak are often used, they are two separate data exposure types. The first one, when coming to the data breach, a data breach is when a successful attack is able to secure sensitive information. A data leak does not require a cyber attack and generally stems from poor data security practices or accidental actions or inaction by an individual. If a cyber criminal identifies a data leak, the exposed data could be used to strategize a successful cyber attack. So, by detecting and remediating data leaks before they are discovered, the risk of data breaches is significantly reduced. The common form of data leak is called a cloud leak. A cloud leak is when a cloud data storage services like Amazon Web Services S3 exposes a user sensitive data to the internet, while AWS does secure S3 buckets by default. So S3 is not an only culprit. Azure files shares and misconfigured GitHub repository can all prove a poor data protection if configured poorly, causing unintentional data leakage. And coming to the next one, the background information leakage is
Sandeep, are you talking on mute?
Ranjita, we wanted Rahul to speak up. So on the mic, so we're just waiting for him.
Hi, Professor. I'm Rahul Tirukovara. So I'll be continuing with the background information. So with 2.9 million apps in Google Play Store, there are no denying fact that the Android market is growing expeditiously. It has leveraged us with countless facilities and opportunities. But on the other side, it has alarmed us about the data threat. Since the Google Play Store does not strictly monitor the application, as seen in the case of the iPhone or App Store, there are highly chances of approval of malicious Android app. According to a survey, nearly 15 to 30 free popular Android mobile apps secretly send the sensitive information of users like contact numbers, voicemails, pictures, etc. to remote servers. Well, about third party of the apps handle data in an enigmatic manner. As people use applications for performing almost every task, including bank, shopping, and booking, it is developers' responsibility to look into the security matters and therefore provide a convenient and secure user experience. So, coming to the data leakage can be defined as transferring certain information from a user device without their knowledge and collecting it as a receiver side, potentially exposing this data to third-party apps on transmission channel in the process. So the ways to prevent data leakage in an Android app are using encryption keys, implementing HTTPs, uh, preventing data caching, and using considering application logs. So here is an example of data leakage in Android. Uh, in the first picture, you can see the information is being copied, and in the second picture, you can see that it is accessed by a third-party app. Coming to the static code analysis, also known as source code analysis, is usually performed as part of a code review, also known as white box testing, and is carried out at an implementation phase of a security development lifecycle. Static code analysis commonly refers to the running of static code analysis tools that attempts to highlight possibility vulnerabilities within static source code by using techniques such as taint analysis and data flow analysis. Ideally, such tools would automatically find security flaws with a high degree of confidence that what is found is indeed a flaw. However, this is beyond the state of the art for many types of application security flaws. Thus, such tools frequently serve a aid for an analyst to help them zero in security relevant portion of code. So they can find flaws more efficiently rather than a tool that simply find flaws automatically. There are various techniques to analyze static source code for potential vulnerabilities that may be combined into one solution. These techniques are often derived from compiler technologies. The first one is data flow analysis. Data flow analysis is used to collect runtime information about the data in software while it is in a static stage. Uh, Coming to the next slide, taint analysis. Taint analysis is a process used in information security to identify the flow of user input through a system to understand the security implications of the system design. This analysis aims to mitigate risks such as SQL injections, which generally arise when other part of the program use user input without proper sanitization. So what does taint analysis checking for? Many languages such as Ruby have taint checking mechanisms baked into them. The way this works is by marking variables that have received user input as tainted. Each variable that derives from them is marked tainted as well. Following this trail, the analysis tool can come up with a list of tainted variables. Finally, suppose a critical operation such as DB call or an OS level invocation use any tainted variables. In that cases, the tool can alert the developer of the potential security risk. So Next is the FlowDroid. So the FlowDroid is a context flow field objective sensitive and lifecycle aware static taint analysis tool for Android applications. Unlike many other static analysis approach for Android, we aim for an analysis with very high recall and precision. To achieve this, there are two main challenges. To increase precision, we need to build an analysis that is context, flow, field, and object sensitive. To increase recall, we have to create a complete of Android's app lifecycle. So FlowDroid uses a very precise call graph, which helps us to ensure flow and context sensitivity. Its IFDS based flow functions guarantee field and object sensitivity because an accurate and efficient ELISA search is crucial for context sensitivity in conjunction with field sensitivity. We want to highlight this part of our analysis, which is inspired by Adomia. So next, the Droid Bench. It is an open test suite for evaluating the effectiveness of taint analysis tools. Specifically for Android apps, the suite can be used to assess both static and dynamic taint analysis, but in particular, it contains test cases for intersecting static analysis problems like field sensitivity, field object sensitivity, trade-offs in access path, lens, etc. As well as for Android specific challenges like correctly modeling an application's lifecycle adequately, handling asynchronous callbacks, and intersecting with the UI. The distribution contains an Eclipse workspace with all source code projects as well as readably compiled APKs. Uh, this is the explanation of the main idea of FlowDroid. Let's see the challenges faced by the FlowDroid. So the challenges faced by the FlowDroid is need precision model of Android lifecycle and their associated callbacks. We cannot determine sources of sensitive information from the code only with the XML files and the code. And also a Java code like a deep complicated analysis and virtual dispatching constructs. So we need highly objective sensitivity to resolve analysis effectively. So the next will be continued by my friend.
Hello all. Hello, Professor. So I'm currently, I'll be describing about the precise modeling of the life cycle of Android applications. And when it comes to the Android applications, in the whole life cycle depends on three main things. The first thing is multiple entry points, and the second thing is asynchronously executing components, and the third thing is callbacks. So firstly, I'll be discussing about the multiple entry points. When it comes to the Java programs, we do have main method to call the functions inside a from inside a Java program. Whereas when it comes to the Android applications, we do not have a main method where we could call the functions like on stop or on resume or the components which could be called using the functions. So apps instead comprise many entry points. So implicitly called as an Android framework. The Android operating system defines a complete lifecycle for all the components in an application. Mainly, there are four kinds of components an app developer can define. Those are activities such as single focused user actions, and the second is services perform background tasks, and the third thing is component content provider, which defines database like storage, and the fourth thing is broadcast receivers listen for global events. All these components are implemented by deriving a custom class from a predefined operating system. And when it comes, these can be implemented using a deriving a custom class from a predefined operating system. And these can be registered in the Android manifest.xml file, and we can override the lifecycle methods too. For instance, when it comes to the methods, for instance, it can stop an application when the memory is totally full in an Android application, and later restart it when the user returns to it. And also, instead, all possible transitions in an Android lifecycle must be modeled precisely. To cope with this problem, FlowDroid constructs a custom dummy main method, which is used to call these all methods at times when user interacts with an application in an Android. And the second thing is asynchronously executing components. In asynchronously executing components, we have like different kinds of activities and in an application and also services. Whereas applications, they may have executed in a sequential order, but couldn't be predefined or couldn't be determined whether they are executing in a sequential order or not. So whereas coming to the services, they run in the background. So activities may launch other activities based on user interactions, while services run as parallel background tasks. So here we introduce FlowDroid, which models this execution by assuming that all components can run in any order. So FlowDroid uses IFDS framework, which is not path sensitive, whereas when we don't use FlowDroid, it becomes a bit more expensive to track each and every program. So whereas when we use the FlowDroid, it becomes a bit easier for us to track and merge all the programs at a single point. And also FlowDroid is not path sensitive, and it can be efficiently analyzed to use the application. It generates as a dummy main method that is used in all possible ways and for all the components and for all the in a life cycle. This approach eliminates the need to traverse all possible paths individually. When it comes to the callbacks are plays a very crucial role in registering and receiving the various types of information events such as location or user interactions. FlowDroid models these callbacks when its dummy main method to identify potential security issues, such as storing sensitive data and later sending it to the internet without proper authorization. So FlowDroid assumes that callbacks can be invoked in any possible order, since the exact order of their execution cannot be predicted. As I've earlier mentioned in the executing of asynchronously executing components, that we cannot determine the execution of activities, but whereas when it comes to the FlowDroid, it can be determined with an particular order of execution. In the similar way, here to maintain precision, FlowDroid associates the components like activities and services with the callbacks they register. For example, an activity may register callbacks that are invoked when a button is pressed. Like in an application, when we press a button, it can be invoked using we can restrict callback on that particular button. And FlowDroid analyzes the respective callback handler between the on-resume, on and on-pass events. Like when we are using an application, we do have different kinds of events registered on each and every button. So in order to stop running of that particular application, we click on the button called exit. So on that particular button, we can assume that there is a function being registered on that particular button, like the on pause or on stop, this kind of events being registered on that particular button. Whereas in order to start the application, we also do have a buttons like start. So while we click on that button, we do have events which are registered on that particular button, like on resume. And these callbacks can be registered on an Android platform. So they can be defined declaratively in XML files associated with an activity, and also they can be registered imperatively using specific system methods. These are the two ways in which we can register callback onto an Android application. So here the FlowDroid comes into picture, which supports both the approaches. Additionally, in the context of malware, in the context of viruses, in the context of different kinds of mess that happens, there is a risk that attackers may register undocumented callbacks, like which are not documented at all. By overriding these methods, the Android infrastructure includes the native code. So FlowDroid can recognize such overwritten methods and treat them similarly to normal callback handlers, like button clicks. So overall, when it comes to the conclusion of the FlowDroid in the callbacks, FlowDroid considers the ordering and association of callbacks with their parent components to accurately analyze the flow of data and potential security vulnerabilities in Android applications. So also we do have the call graph, which is used to incrementally extend and include these newly discovered callbacks, and scan as run, since callback handlers are free to register new callbacks on their own. And I conclude by this saying that FlowDroid is a static analysis tool which is mostly used to approximately and precisely register the callbacks, as well as asynchronously execute components, and also use multiple entry points in the Android application. Thank you, and I hand over it to TV. Thank you all.
Hello everyone, now I am presenting the precise flow sensitive analysis. Precise flow sensitive analysis is a technique used in static program analytics to analyze the behavior and properties of a program by considering the flow of data and control within the program. One of the major difficulties in the analysis is to implement the high object sensitive to resolve aliasing effect. As we can see in the figure, the FlowDroid combines the forward tenant analysis and on-demand backward analysis due to the BF in the tenant at the risk. Whereas we can see the step 1, the tenant variable W is propagated forward, training the heap object x.f. And we can see the step 2 continues to the tenant tracking for W and x.f in the implementation. Whereas in step 3, it is most important, whereas heap object gets tenated, the backward analysis sets upward for aliases of the respective object. Whereas the process goes on, we can see the last step, number 7, b.f is found and the propagated forward as normal tenant. Next, aliasing. Aliasing refers to the situation where two or more different names or references are used to access the same object. In other words, we can put it in multiple variables or references point to the same underlying data. When aliasing occurs, changes are made to one aliasing will affect the data ascending through the other aliases. Whereas we can see the source code here with the variables a, b, c and d.f. all are referred to the same data, whereas first we initiated A to the source, and B is initiated with A, C with the B, and D dot F with the C. Next, aliasing analysis. Analysis is given Android app is expensive and imprecise. It also analyzes the variables that are not necessarily alias of source. So we end up keep tracking a lot of more aliases than we need. On-demand aliases for tenured information only is needed to avoid this problem. On-demand analysis. Whenever a tenured value is assigned to a heap location, such as a file or an array, FlowDroid searches backwards for aliases of the target variable. When a tenured variable assigned to heap location variables, for example, in a field, class, or an array, we need to go and find aliases of the heap allocated variable on top of such variables. Context sensitivity. The algorithm representation assumes the reader to be familiar with the algorithmic description of the original IFDS algorithm. More precise, high-cost static analysis technique. Context insensitivity analysis would know that A and B are associated with add5 function, but it does not know the B is still at 1. That means it is unstable. Whereas in context sensitivity analysis know that B1 is unchanged. It remains constant and only the A value keep changing, and it will change to 5. Maintaining cost sensitivity. Here we can see the diagram analysis handover with context injection in tenant. Here the black nodes represent the data flow facts before and after the representative statements, and the black red edges represents data flows, and the fact 0 is a tautological fact that is always true. The left hand side of the figure shows how the forward tenant analysis determine x dot f of the tenant, whereas the processing of assignment x dot f forward analysis spams an instance of backward analysis shown on the right hand side. This shows the difference between the forward and backward analysis of the context sensitivity. The maintaining the context sensitivity. In the second diagram, second problem, it is avoided to use false positivity due to the unrealizable paths. The FlowDroid needs to prevent the backward analysis to return into the context, not analyzed by the forward analysis, whereas the forward analysis is worked in the vice versa. To implement these constraints, the backward analysis is FlowDroid actually never returns into the caller at all. In coming to the algorithm main loop of forward solver. Here we have two algorithms. One is forward solver and second one is backward solver. Here we can see the forward solver algorithm. The algorithm assumes the reader to be familiar with the algorithmic description of the original IFDS algorithm. Both solves operate on their own work list containing so-called path edges that summarizes the data flow. Whereas we can see in the algorithm 1, or step 2 pop SPD D1 tends to N D2 of workflow list. So upon fair current statement node N, an edge effectively states that analysis concludes the D2 holds at n if D1 holds at the start point SP of n's procedure P. Whereas in context injection happens both the ways, uh, both in the forward direction and backward. At the line 9 in the example, we can see the backward analysis pass or a forward analysis of out.f. It injects into the forward analysis the original context in the algorithm 2. We can see it in the line 17. Insert SP, D1 tends to N, D3 into workflow list, whereas the backward analysis descends into a call. It will evaluate span forward analysis with reaching the method header. The forward analysis can then make sure to only return into the right colors because its context is injected into the backward analysis. Next part implementation, my friend Akhil will present it.
Yes. Hello, Professor. Hello, everyone. So the implementation of the FlowDroid is just like a tool that analyzes Android applications to identify the lifecycle and callback methods within the code, as well as the calls to it calls to sources such as the sensitive data and sinks such as methods that handles the sensitive data. Once the FlowDroid is identifies these elements, it generates a duplicate main method based on the list of lifecycle and callback methods. This duplicate main method serves as an entry point for the analysis. By analyzing the code starting from the main method, the FlowDroid is able to construct the call graphs. Overall, the FlowDroid combines these analysis techniques to provide insights into the data flow and control flow. Uh, helping to it tries to help the identify the potential security vulnerabilities and privacy concerns. The next slide. Yeah. Once the FlowDroid identifies the sources of sensitive data, such as the user inputs or device information, it performs a taint analysis to track how the data propagates through the application. This analysis involves traversing the inter-procedural control graphs, which is said to be ICFG. Once this analysis is complete, the FlowDroid generates a report that includes information about all discovered flows from the source to the sinks. This report provides a detailed account of the paths through which the sensitive data flows, allows the developers to understand how and where the potential data leaks and the security vulnerabilities may occur. The next slide. Yeah. So the shortcuts of native library calls is when performing static analysis on the entire Android framework, the process can be time consuming. To address this, the shortcuts may be used for the better use of the analysis. These shortcuts involving adding uh, taints to the predefined set of library calls rather than analyzing the entire framework. By focusing on these specific library calls, the analysis can be more efficient and targeted perfectly and reducing the overall time required for the analysis. So the native calls is actually treated as a black box, and during the taint analysis process, by default, it is if any parameter of a method call is marked as a tainted or sensitivity, both the call arguments and the return values of the method are also considered as tainted. This means that if any sensitive data is passed into the method as an argument, the analysis assumes that this method is a manipulative method, and there is a possible limitations in this native calls. And the next slide. Yeah, the intercomponent communication. The FlowDroid approximates explicit intercomponent communication in Android by considering methods that sends intent as sync and callbacks that receives intent as source. This allows FlowDroid to track the flow of the data between different components of the application. However, the Android also supports implicit intent-based communication, where the result values are of a called activity is automatically passed back to the calling activity by the operating system. This type of communication is not fully captured by the FlowDroid current approach. So to address this limitation of the and improve the precision of the inter-app communication analysis, there is an ongoing work going on to integrate FlowDroid with EPICC. EPICC is a static analysis tool that utilizes like suit and heroes to perform string analysis, allowing more accurate resolutions to inter-app communication. And by integrating FlowDroid with EPICC, the goal is to achieve the analysis capability and provide more precise understanding to inter-app communication includes the overall accuracy and effectiveness of analysis Android application to potential security vulnerabilities and data leaks. The next slide. Yeah, the limitations are the intercomponent communication exchanges the data, messages, function calls between the software component, and there is a unsoundness limitation which in the violation of correctness and reliability properties, leading to the unpredictable behavior of the uh, system, and probabilistic taints in multi-threading, challenging in handling uncertain data propagations in a concurrent environment. And the next slide. Yeah, the reflective calls with constraint strings arguments. This is limited to handling the reflective calls where the argument passed as a constant strings, and the external configuration file are these reflex calls rely on the external configuration file to determine the method uh, to be invoked at the runtime. And there is an alternate approaches for these limitations. When reflective calls with non-constant string arguments are required, alternate techniques may be necessary due to Android limitations. And then the next slide. Yeah, when it comes to multi-threading, it can't handle the leakages in FlowDroid tool. The next slide. Yeah, the experimental evaluation will be explained by my friend Ranjita.
Hello, everybody. So I'll be talking about the experimental evaluation of the FlowDroid. So for evaluating FlowDroid, there was a research questionnaire that was set up. Like there were multiple questions that were included. The first question was in terms of precision and recall, how this FlowDroid is compared to other commercial taint analysis tools in Android. Like analysis is tracking how private information flows through the project and if it is leaked to the public or not. And the second question was, does FlowDroid find if privacy is affected in the secure bank? Like, will it challenge vulnerability detection tools for Android? And if it is also about its performance. Um, and the third question was, next slide, please. Uh, does it also work in real-time applications and also about its fastness, like how fast it is able to detect? And the fourth question was, what is its performance like when it's being applied to Java related taint analysis problems, and not Android again, and in terms of precision and recall specifically. Like precision in terms, when we say precision, it's like percentage of your results which are relevant to what is required. So based on these four questions, the evaluation was done for the FlowDroid. Um, and then evaluating, then there was evaluation done, like how is FlowDroid with Droid Bench together work. Like when we say Droid Bench, it's nothing but it's like a open test suite for evaluating the effectiveness of this taint analysis tools, like specifically for the Android apps. Um, so on this droid bench, this flow droid like finds a very high fraction of data like that leaks while keeping the rate of false positives low. Like how this flow droid works on the droid bench to keep the false positives, sometimes it detects something which is actually not true. So those things, it helps in keeping it low. And then when this FlowDroid works on droid bench, like we can say it is achieving like 93% and 86% of the recall and precision respectively. And it's actually outperforming the commercial tools. Like for example, in case we can say about IBM App Scan Source and 45 SCA. So FlowDroid is really working good with Droid Bench was the evaluation that resulted with. Next slide, please. So continuing with these questions, what was done? There were a lot of evaluations on the FlowDroid. Like if we have to say, it was like uh, the precision measure for this FlowDroid was 81%, as we already spoke, and the precision on the app scan was 74 percentage, and it finds like the data leaks verified by the insecure bank was like numbered seven. There were seven data leaks, and uh, like successfully finds leaks in a subset for like about 500 apps. If we have to name, like from the Google Play, and if we have to talk about virus share project, there were at least many numerous malware apps. Like if we have to number it, there were 1,000 of them, and there were many more reasons. um, but the authors of this research paper were unable to actually evaluate every single taint analysis tool for Android of your own. Next slide, please. So regarding the first question of the research questionnaire, if you see the image pasted in this, there's a column called TP. This column actually shows the true positives, like which means the actual leaks that this app found is shown on the TP column, and the FP column actually shows the false negatives, which is relatively low. This is how like FlowDroid is really beneficial when compared to the when we see the false positives, the number is really low. Next slide. Next slide, please. So, based on these evaluation methods, um, like these malicious applications, what were found out, the developers they just chose like less well-known sources, and the analysis tools, how it syncs, how this app syncs, uh, and then it's all also they generated the comprehensive list of the sources, and then the malicious behavior in these applications, how it syncs with these malicious behaviors. And uh, there were like few well-known methods like for obtaining and sending out potentially sensitive information. All these lists were made. Next slide. um there is like there were the developers used many avoiding like how some things which actually avoided detection. So if you see on the right side the image shown, it's the source code the developers actually wrote. So if you go to the line, if you see the line 9, it's actually returning the cell ID, and the line 11, the right line right next to it, it's actually returning the location area code. So both these are actually trying to service the current like GSM cells what we are talking about. And then in the image, if we see the line 12, this line is actually checking for the cell tower ID. The actual malicious app would perform a lookup in this, like in this list, what we get in this Berlin. This is how the code looks like. Next slide, please. So this slide talks about how Fortify and like how our app is compared to Fortify SEA. So this Fortify SEA actually shows problem like how IBM apps can works, right? It is similar to this app, like it handles various life cycles and callbacks of the Android components, and then like the tests which are performed by these this Fortify SCA, uh, like it involves static field, like which treats like the coincidentally causes the leak, and to be reported, it will be reported. And then this actually is developed by HP. It's like it's actually, if I have to say, it's a commercial tool. It's used for security analysis. Next slide, please. So that was about the question one. So the while evaluating the question two, that was based on insecure bank, it's like it was about about finding the vulnerabilities this particular Android app created was creating um, in the evaluating analysis, like what we spoke about, the FlowDroid in specific. And this insecure bank also it used Intel Core 2 Centrino CPUs and 4 GB of physical memory, like which was actually running on the Windows 7. It was running with the Java version 1.7. These are the minute details of the apps that were used for this application. Next slide. While evaluating the question three, which was based on can the FlowDroid work on the real-time applications? While evaluating that, it was found that the many types, like many apps were exposing private information, like in case, like we can say IMEI or local information or log files, they were being exposed. And uh, also this Samsung push service, it records phone IMEI, which was also noticed while the evaluation. And um, the operating system, it doesn't place the same restrictions on the logs, like it has a different set of restrictions for the logs on the files, and it's not the same on the logs. So it's actually problematic in case of Android 4.0 or older devices. That's what was found in terms of real world applications with FlowDroid. Next slide, please. So on the question 4, which was basically on the Security Bench Micro, this was created for Android, and this app what was found like it was like it had a precision in the Android area, like because it's thorough and accurate, like in handling Android's life cycle. That was really a good positive point. And then the FlowDroid was also evaluated against many more software versions. If we have to name, it was Stanford Security Bench Micro, which was versioned 1.08, and J2EE micro benchmarks, 96 of them, and then for the web applications, all these versions of softwares were test evaluated against. Next slide, please. So there were some enhancements that were found out like after the evaluation process. Uh, the enhancements were there were two enhancements. One is implementing annotations for virtual dispatch, and the other was pre-filtering. So when we say implicit annotations for virtual dispatches, it's like it's based on Weka. Like they found that when these methods were being annotated to obtain this training data, what was used, and it was beneficial to propagate method annotations, high and low, and the class hierarchy in these cases, like which were actually inherited. So the other enhancement was pre-filtering. Here, it was justified by the fact that the apps can access methods only through reflection. Next slide, please. So I'll be handing over to my next teammate to continue with the related work. Thank you.
Okay, hi. Now I'm going to discuss about the related work of this topic. There are several approaches to static analysis of Android applications, differing in precision, runtime, scope, and focus. One of the most sophisticated ones is checks. It is a tool to detect component hijacking vulnerabilities in Android applications by tracking taints between externally accessible interfaces and sensitive sources or sinks. Although not built for the task, checks can, in sources or sinks, be used for taint analysis. Checks does not analyze calls into Android framework itself, but instead requires a hopefully complete model of the framework. In FlowDroid, such a model is optional and, except for native calls, is used only to increase precision and performance. Users can thus omit this model entirely and still be sure not to lose taints. Check's entry point model requires an enumeration of all possible split orderings, which is not necessary in FlowDroid. Furthermore, checks is limited to at most one object sensitivity, while FlowDroid's demand-driven analysis allows for context of arbitrary lengths using a default. We have found one object sensitivity to be too imprecise in practice. Next slide, please. Leak Miner. Leak Miner appears similar to our approach from a technical point of view, like FlowDroid. It is based on Suite, uses Spark for call graph generation. It implements the Android lifecycle, and the paper states that an application can be analyzed in 2.5 minutes on average. However, the analysis is not context sensitive, which precludes the precise analysis of most test cases in Droid Bench. Next is Android leaks. This also states the ability to handle the Android lifecycle, including callback methods. It is based on Vala's context sensitive system dependence graph, with a context insensitivity overlay for heap tracking, but is not as precise as FlowDroid because it taints the whole object if tainted data is stored in one of its fields. That means it's neither field nor object sensitive. This precludes the precise analysis of many practical scenarios. Next is ScanDroid. It is another tool for reasoning about data flows in Android applications. Its main focus is the intercomponent example between two activities in the same application and also interapplication data flow. This also poses the challenges of connecting intent senders to their respective receivers in other applications. Whereas Scandroid prunes all call edges to Android operating system methods and conservatively assumes that the base object, the parameters, and the return value to inherit taints from arguments. This is much less precise than FlowDroid's treatment. FlowDroids applies this default rule only for native calls, not model explicitly. FlowDroid currently models intent sending as sink and intent reception as source, yielding a sound treatment of interapplication communication. In the future, we plan to integrate FlowDroid with Epic. It is a novel static analysis that uses string analysis to precisely resolve interapplication communication. And next slide, please. And other approaches like CopperDroid dynamically observe interactions between the Android components and the underlying Linux system to reconstruct higher level behavior. Special simulation techniques are used for exercising the application to find malicious activities. CopperDroid automatically and accurately reconstructs events of interest that describe not only well known operating system interactions and also for example file and process creation but also complex intra and inter-process communication, likewise SMS reception and so on, so whose semantics are typically contextualized through complex Android. And attackers, however, can easily modify an application to detect whether it is running inside a virtual machine and then leak no data during that time. Alternatively, data leaks might only occur after a certain runtime threshold. Orasium and Diode scope largely suffer from the same shortcomings with respect to static leak detection. Next slide, please. Next is Trandroid. It identifies sensitive data, taints, and tracks data flow via variables, messages, methods, and files. Taindroid is one of the most sophisticated Android taint tracking systems to date as a dynamic approach. However, it yields some quite different trade-offs compared to Flowbird. For instance, Taindroid has no problem tracking taints through reflective method calls as Taindroid is implemented as an extension towards the execution environment for which it does not matter whether methods are invoked through reflection or not. On the other hand, we can also say that it is used for triaging malware before installation time. Then train diode can successfully detect malware only if paired with dynamic testing approach that yields decent code coverage. Static ahead of time analysis like Flowbird does not share this shortcoming because they cover all execution paths. Secondly, a dynamic approach such as Taindroid can be fooled by a malicious apps that recognize that it is being analyzed, in which case the application could simply refrain from performing any malicious activities. While this is not problematic because if it is the dynamic analysis is installed on the user's end's mobile phone, in that case, so that the malware would effectively be tamed by the user. It is problematic if the dynamic analysis is only used for ahead of time triggering of malware that could then later on be installed on the system and not protected by the dynamic analysis, in which case the application could resume its malicious activities. Static approaches such as FlowDroid does not share these particular shortcomings as they never actually execute the application. Next slide, please. F4F. It is the framework for performing taint analysis of framework-based applications using a specification language called WAFL for describing the functional behavior of the respective framework. While originally created for web applications, it might also be extended to model the Android framework by adding a WAFL generator for Android. FlowDroid's dummy main generation has the big advantage to only include components and callbacks that are indeed accessed by the application. This, however, requires a semantic model of the application's manifest, the layout XML files, the compiled resources file, and application source code, which are all interleaved. F4F could at best be used to give a coarse approximation modeling for the common denominator of all possible applications. And FlowDroid currently handles exceptional flows through a coarse over approximation. Kastrinas and Samarda 6. These are the researchers that have recently presented a novel and particularly efficient approach for analyzing exceptions and point to point analysis in combination. It would be interesting to see whether FlowDroid can easily benefit from an integration of some of these concepts. Although F4F could only provide a rough approximation of the common denominator of all potential apps. And next, one of the researcher, Rontev et, have also proposed a way to pre-compute summaries for large libraries with the intention to speed up the repeated analysis of client code. For Android applications which come with a huge Android framework, such as an approach make a lot of sense. Roundtwo's work is based on the IDE framework, which Flowbird also uses internally to conduct its IFDS based analysis. It should therefore be entirely possible to incorporate the author's ideas into the Flowbird. Next slide. So next, Dilling is the another researcher who have developed an approach to more precisely analyzing the contents of collections and arrays. The required analysis effort is non-trivial, but given our results, it is clear that FlowDroid could increase its precision further by implementing analysis supports along those lines. And next slide, please. Okay, the sushi part will be taken lead by my teammate.
Yeah, hi, Professor Harigovardhan here. So I'll be covering from the part Sushi. So Sushi is a tool for the fully automated classification and categorization of Android sources and sinks. Now let us discuss more on what are Android sources and what are Android sinks. So basically, sources and sinks refer to specific points in an application where data is either inputted or outputted. So when the data is inputted, it is known as a source, and when the data is outputted, it is known as a sink. So let us see few examples of the source. This includes the input from the various input methods such as keyboard input, voice commands, sensors, camera, microphone, and moreover, this also includes data received from APIs, web services, or other network protocols. Now coming to the examples of sinks, sinks can be logging mechanisms used to output data, which includes log files, console outputs, displays, databases, or external storage. And to get more deep understanding about SUSI, which uses a supervised learning for classification tasks, it involves training a classifier using a small set of manually annotated training examples. This trained classifier is then used to predict the classes of new unseen test examples. The classification process relies on the set of features where each feature is a function that evaluates a specific criterion for an example. And the approach assumes that there is a significant correlation between the examples in each class and the values obtained by the feature functions. For example, let us consider an example in the context of estimating the risk. of a driving accident for an insurance company. So here the majorly three features may be identified. Number one, the years of experience that the driver has. And number two, the blood alcohol level. And number three, the driver's phone number. So the learning algorithm determines that higher experience levels are negatively correlated with the accident rate, while alcohol level is positively correlated and the phone number is unrelated. So the impact of a feature on the overall estimate is determined by its distribution of values in the annotated training set. If there are many examples of accidents with high alcohol levels, the alcohol feature will be given a greater weight. However, if there are no more accidents involving inexperienced drivers in the training set than alcohol related accidents, then the experience feature will be ranked higher, obviously. So the example further demonstrates the classification process. A simple rule-based classifier infers that reports with alcohol levels greater than zero point 0.2 are associated with the accidents. Therefore, C2 in the test data would be classified as accident is S. However, further reasoning is required for considering the experience level. Here, there are two test records of inexperienced drivers with levels of 0.2 or below, one with an accident and one without. In this case, the classifier would choose randomly because both accident S and accident no are equally likely. Next slide. Yeah. Alternatively, a probabilistic classifier might choose accident S since accidents are generally more likely for inexperienced drivers in the given test data. This illustrates that different classifiers may produce different results based on their underlying principles and approaches, which is used to predict the class of an arbitrary number of previously unseen test examples. So this classification is performed using a set of features. Next slide, please. So now let us talk about the Sushi's design approach. So here, as we can see in the figure, it consists of four components known as input, preparation, classification, and the output. So all these combinedly called as the layers. So the design approach, it involves as a four layers. The process is similar. The design approach can be summarized as follows. Now let, let us discuss about the input layer. The input data consists of Android API methods that needs to be analyzed. The input data is divided into a set of hand annotated training data for classification and set of unknown test data. A database of features is required for both classification as well as the categorization. Now, let us discuss about the second layer known as classification or preparation. So, Sushi uses supervised learning to classify methods as sources and sinks, or neither. Features are evaluated on the training data and the test data. The first matrix is built using the training data, and the second matrix is built using the same feature set applied to the test data. And Sushi trains the classifier using the first matrix and applies it to the records in the test matrix. Let's talk about the categorization layer. Like Sushi categorizes the previously identified sources and sinks both in a separate manner. The sources and sinks from the first step are treated as the new test sets. Hand annotated training data is provided, categorized based on semantic categories related to the mobile domain. Here, different features are chosen for the different databases, like for the feature databases. Sushi applies the classification approach to categorize the sources and sinks. So now let's talk about the output layer. The final output consists of two files, one for categorized sources and one for categorized sinks. So here different categories are defined for sources and sinks, representing various aspects of the Android API methods. Some categories refer to data managed by applications, not the operating system itself. Each category includes some specific relevant methods, while which a method is not fitting in any of the category are labeled as no category. And moreover, it is important to note that categorization involves two distinct classification problems. So one is for the sources and one is for the sinks. The correlation between features and categories may differ significantly for sources and sinks based on the input we take. So next slide, please. So to give a conclusion on this, so there are a bunch of static taint analysis tools available, but with certain limitations. So now what is static taint analysis? The static taint analysis tools are the software analysis tools that examine the flow of data within a program's source code to identify potential security vulnerabilities related to the information flow. And FlowDroid, which is specifically designed for leakage detection in Android, as we already aware of that. And it also offers higher precision, improved sensitivity, and better modeling for the application lifecycle. So SUSI, which combines trained analysis and machine learning categorization approaches, while FlowDroid detects potential leakages, SUSI further analyzes the results. On-demand algorithms ensure FlowDroid to maintain the efficiency despite of its strong context and object sensitivity. These algorithms are designed to be activated only when needed, optimizing the performance of the tool. FlowDroid has been evaluated using the Android-specific benchmark suite called Droid Bench. The purpose of this evaluation was to compare FlowDroid with other commercial tools such as AppScan Source and Fortify SCA. FlowDroid demonstrates a higher precision rate of 86%, which means it has lower number of false positives. This indicates that FlowDroid is more accurate in detecting potential leakages without generating unnecessary warnings. Droid Bench will become a widely accepted standard test set for Android trained analysis in future. This implies that Droid Bench has the potential to serve as a common benchmark for evaluating the effectiveness and the performance of different trained analysis tools for the Android applications. Next slide, please. Yeah, it also analyzing tool that merges the trained analysis and machine learning categorization approaches. And it also, and the FlowDroid also detects the potential leakages. And coming to this slide, this is mainly the Android specific benchmark suite and the Droid bench and use it for comparing FlowDroid to the commercial tools. So that's all we do have for the conclusion. The next slide. So these are the references we have taken from here, which has been mentioned over here. Any questions, you're welcome. Thank you, Professor. Thank you all.